Two questions before we begin. Keep them within reach. First, why does a sharper simulation always cost more computer time? Fast or accurate, pick one. That is the deal we've all accepted. And second, what actually breaks when you tear out the physics formula and put a neural network in its place? Hold on to both. Now, a party, you're catering 1 to 100 guests, and your job is to predict before anyone arrives whether the evening works. Enough food, enough drink, nobody's stranded in a corner. The exact way, simulate the evening, track every conversation, who drifts toward whom, which pairs cluster, which groups avoid each other. But with 200 guests, the possible groupings multiply beyond any notebook on earth. Nobody plans a party that way. Here is what the caterer actually uses, a headcount map, where the room will be crowded, where thin. From that one map, almost everything follows. Using a rulebook, and the rulebook works except for one stubborn line, the correction for how people actually mingle, how they bunch, how they dodge. Nobody has ever written that line down exactly. And for 60 years, one pattern has held. Every sharper version takes longer to compute. So here is the prediction nearly everyone makes. Maybe you are making it right now. That is simply the price. A sharper estimate must always take longer. Accuracy is bought with time. Take a moment. Is that a law or just a habit? Because the missing line this paper claims is not something you derive at all. It is something you learn. From Microsoft research, a functional called Scala, and the anchor question of the next quarter hour is the so-called divine functional something you derive, or something you can learn. Let's find out. Swap the party for a molecule. The guests become electrons. The room, the space around the few atomic nuclei. And does the evening work becomes, what is this molecule's energy? That number is the glue between atoms. Get it right and you know whether a reaction proceeds. Whether a drug candidate binds its target, whether a material captures carbon, whether a flow battery holds up. Get it slightly wrong, and the lab wastes months chasing ghosts. The exact method exists, the Schrödinger equation, the every conversation plan. It tracks all the electrons jointly, and its cost grows exponentially with their number. 10 electrons find a drug molecule. Forget it. Not impossible in principle, impossibly expensive in practice. Hold on. If you keep only a map of where the electrons are, haven't you thrown away the physics? A head count can't know what everyone is doing. Completely reasonable and probably wrong. That is the shock. In 1964, Hohenberg and Kohn showed the density is enough. Exactly enough in principle. Density functional theory is not an approximation. It is a reformulation. The catch is not that the map is lusty. The catch is that nobody knows the formula that reads it. A rule that eats an entire map and returns a single number. Mathematicians call that a functional, a function of a function. And here is the move that made it practical. Split the energy. The big pieces, electrostatic repulsion, kinetic energy, the pull of the nuclei, all computable exactly and cheaply. The bill grows like n cubed. Everything mysterious is swept into one small leftover. The exchange correlation energy, the mingling correction small. But it decides the chemistry. How sharp does that term need to be? About 1 kilocalorie per mol missed by more. And a predicted reaction can simply flip. Chemists call that bar chemical accuracy. Against it, 60 years of handwritten rule books, hundreds of them. A whole zoo have all fallen short somewhere. One leftover term. That is the whole war. Here is the field's own map of those 60 years, figure 1, straight off the page. On the left, the density in the middle. Features read off it at grid points. Real functionals chop space into a grid, 10,000 to 1,000,000 points per air molecule, and evaluate the correction point by point on the right. Out comes the energy. The rungs have names. Chemists call this Jacob's ladder. The 60s and 70s, only the density at each point. The 80s and 90s add its slope, then its kinetic texture, still cheap, still n cubed. Then the expensive turn, the hybrids borrow a slice of the exact conversation tracking. And the bill jumps to n to the 4th. Double hybrids n to the 5th. 60 years of climbing, and the field has a nickname for the summit, the pursuit of the divine functional. Notice what the ladder quietly teaches: accuracy and cost climb together. Every rung up is a sharper formula and a steeper bill. Exactly the deal from our first question. One caution, those n cubed n to the 4th labels. Not what the deal grows, not what it is. Hold that near the end. We'll stop trusting labels and actually measure. Before we go further, commit to something your simulation misses by 5 kilocalories per mol. Which piece do you blame? Option A, the electrostatics. Option B, the kinetic energy. Option C, the little leftover, pick one. not option A and not option B. Those are computed exactly, the blame lands. Almost every time on the leftover, one small term carries the whole error budget, which is why this film is about that term and nothing else. So meet the cast properly, the density, rho, the headcount itself. Its slope, how sharply the crowd thinks, its kinetic texture, tau, the leftover, the exchange correlation energy. And one newcomer with no formula at all, F theta, a dial, waiting to be learned. Suppose you agree that dial should be learned from data. How would you train it? Two plans come to mind first, and both fail in ways that teach you what the real solution must look like. Easy. At every grid point, fit a curve. Feed in the local features, density, slope, texture, and train a little formula to output the correction point by point. More parameters, better fit. No. It has been tried for years, and it tops out, because the true correction is not local. What the electrons do here depends on the density over there. And the point-wise rulebook, however many parameters you give it, cannot see over there. With only scraps of gold-grade data available, machine learning stayed stuck exactly here. The most famous attempt, DeepMind's DM21, did better by borrowing the ladder's expensive ingredients. It reached roughly 4 kilocalories per mol on the standard exam, but the paper's own footnote deserves repeating precisely. That model and its successors were trained on portions of the very benchmark they're graded on, and they pay more than hybrid prices impressive, and not apples to apples. Fine. Then no hand-holding, drop a big network straight into the real simulation loop and train it there, end-to-end, right? Except the loop uses a functional to find the density in the first place, guess a map, score it, reshape it, repeat. On day one, your network is random noise. It corrupts every map it touches. The loop diverges or settles on garbage, and you'd be running that loop for every one of 400,000 training examples unstable and unaffordable. So here's the design question. This paper had to answer, try it before I do. To beat plan A's ceiling, grid points must talk to each other. If you let all of them talk to all of them, how does the bill grow? And is there a cheaper conversation that still works? Hold that thought, really hold it. All-to-all talk among 100,000 grid points means conversations that grow like n-squared bolt that onto every energy call, and you've climbed straight back up the ladder. Scala refuses, watch what it does instead. This is the actual architecture, figure 1b, stage 1. Read the same cheap features. The third rung reads the density in its two electron populations, spin up and spin down. Its slope, its kinetic texture, stage 2. Process each point on its own. Stage 3, the trick, every grid point talks to one hub. A coarse point parked at its atom. Tables don't chat pairwise. Each table reports to its captain, and the captain's digest comes back down to its own tables. The rest of the room already rides in the numbers every table reads. Stage 4, combine and read off the dial. And that dial sits inside the formula you already have on. Take the very first rungs, exchange energy. The oldest, simplest line in the rulebook can keep its skeleton. Now multiply it point by a learned factor F theta. Bounded, it can stretch the old answer. But never to infinity, that bound isn't cautioned. It is physics. Welded in, it enforces a hard floor called the Lieb-Oxford bound. It keeps two far apart molecules independent. And it preserves how the formula must behave when the density is squeezed. Wait, the entire network is 385,000 parameters. The autocorrect on my phone is bigger than that. It is, and it is deliberate. This dial gets evaluated at every one of 100,000 grid points on every pass of every simulation for every molecule. Small isn't a compromise, small is the price of admission. It is what keeps the whole bill growing like n cubed. One honesty chip before we move on. The long-range stickiness between molecules dispersion is not learned Scala bolts on a standard correction called D3, like most functionals on the cheap rungs. The learned part aims squarely at bonds breaking and forming cheap features, learned conversation. That is the mechanism. Now, the part most telling skip, how do you train such a thing? In use, the functional sits inside a loop, guess a map, score it. Let the scorer reshape the map around and around until it stops changing. Self-consistency, the functional doesn't just grade the map, it helps draw it. Which means there are two ways to be wrong. Your formula can be wrong on a perfect map, or your loop can settle on a warped map. Two dials, wrong rulebook, wrong headcount. And watch, they can cancel better and better scores on a worsening map. In 2017, Medvedev and colleagues caught modern functionals doing exactly that. In their words, strain from the path toward the exact functional, a cheat that passes the exam. Honest training has to forbid it. Remember plan B? Now you can say why it was doomed, training inside the loop from day one hands. The network both dials at once and invites it to turn the headcount dial to hide its rulebook errors. So the training splits in two. Stage 1 never runs the loop, frees the maps, borrows from B3 lib. Yesterday's workhorse and train on one thing only: gold standard energy differences. 400,000 of them, mostly Microsoft's new collection reactions, ionizations, 120,000 molecule in total. Atoms' energies, answer sheets computed with coupled cluster methods, trusted to about 1 kilocalorie per mole, and affordable only for small molecules. And notice differences, not totals. The answer sheets are sharpest on differences, so that is what it learns. Then stage 2, short and careful. The functional runs its own loop now. Training on the maps it actually draws. No gradients through the loop. Draw, gets scored, adjust. And watch both dials. Figure 3. The first 2,000 steps are shaky, then it locks in, and both curves fall together. Energy error down, density error down with it, measured by dipole moments. How lopsidedly a molecule's charge sits, one of the few fingerprints of the map that experiment pins precisely. On that test, it ends below every hybrid. Both dials at once, evidence against the cheat, not proof, but exactly the signature the true functional would show. Quick check before the reckoning. Stage 1 froze the maps. Which dial did that freeze? And why does that make it safe? The headcount dial, with frozen maps, the network can't warp densities to flatter its score. It must learn the rulebook honestly first, then earn back the loop. 2 errors, 2 stages. Now, the reckoning 3 charges, and you should want all 3 answered before you believe a single benchmark number. Charge 1, it memorized the test. First, the paperwork, every molecule bigger than 2 atoms sharing a skeleton with the exam was struck from training. But here's the sharper witness, a benchmark of deliberately absurd molecules, random atoms bolted together. Invented to punish memorized habits. Before I answered the charge, you answered, what did we build in that could handle molecules like this? The classic workhorses on this wall missed those by 25 to 36 kilocalories per mole scala, about 2.5. You don't memorize your way to that cheap features plus the hub conversation, a rule that travels even to molecules that shouldn't exist. Charge 2, a network breaks physics the moment it leaves its data, partly true. And the paper shows you the break, which is exactly why I trust it. Quantum mechanics has a rule. Correlation makes electrons dodge, dodging makes them faster. So one kinetic piece of the correction can never go negative. Train Scala on one single kind of data, the blue curve, and it dives below 0, rule broken. Feed it the full collection, the pink curve. And the rule reemerges unprompted, landing close to the best reference values chemists have reconstructed. Nobody welded that rule in. It was bought with data. The bound and the size rules are welded. This one was learned and off the map entirely. The skeleton is still that old first rung formula. Worst case, it degrades toward ordinary cheap D, FT, not toward nonsense. Charge 3, and this one is yours. A functional that wants to cheat, which of the 2 dials does it hide behind? The headcount dial warped the map to flatter the score. Precisely what stage 2's dipole watch was standing guard against. One technicality, spoken once in the generalized framework scala, lives in that kinetic rule had even more freedom to fail. And it held anyway, charge dismissed with the condition, keep watching the densities. Every release. So look back at our 60-year takeaway, sharper ingredient, costlier formula, strike it. The real claim, accuracy is bought with data. And that answers question 2 in full, 3 things broke. The loop, the data budget, the guarantees 2 stages fix a loop. 400,000 gold answers fix the data, welded rule. Plus, rules that emerge fixed the physics. Time to grade it, but first commit once more, you hold gold answer sheets, trusted to a kilocalorie. What must the exam measure? Option A. Total energy is option B. Energy differences, option C. The full every conversation description, the wave function. Differences, reactions, barriers, bindings, that is what chemistry is. And where the answer sheets are sharpest. Totals are softer ground, the wave function. The exam can't even see. The headline picture, every dot is a function of the axis. One number weighted error over 55 families of problems. And lower is better, the hybrids in blue 3 to 6.5. The cheap rows 5.5 to 8.5. And on the cheap row, a pink dot, before I read its number, say what it is doing down there. 2.8, below every hybrid, at a fraction of the price. That is where the 60-year diagonal snaps. Zoom out to the full wall, all 55, first place medals, 32 of 55, more than every other functional combined. Now, the honest box is self-interaction problems. Its worst family, 12.7. The best hybrids genuinely beat it there. Fullerene isomers beaten by plain B3 lib. A paper that shows its losses is a paper you can calibrate against. The hardest exam, 200 brutal molecule into atoms energies. The 183 well-behaved ones, 0.92 under the bar, all 201.23, dragged by 17 multi-reference cases with no training data. A gap the authors named themselves one boundary, said plainly. This wall is main group chemistry. Transition metals get a preview. Materials aren't graded. Why does it work? 2 surgeries. Cut the hub conversation. The error roughly doubles. Grow the data, thermochemistry, then barriers, then weak interactions. And the error walks down step by step, more data, better functional, systematically. That is the new ladder. And its rungs are data sets. And the Bill measured log scale molecules up to 900 atoms. Before the reveal, place your bet if the 60-year rule is really dead, where must Scala's line sit? Right? On top of the cheap rung standard workhorse, within about 30% on a graphics card, while hybrids run 3 to 6 times dearer and couldn't reach the biggest molecules in this setup. An ordinary processor about twice the cheap price for small ones, shrinking as they grow, one small total. It runs a touch less smoothly than the old formulas, within acceptable range. Sharper at cheap run cost measured. It is already being wired into the standard chemistry packages, one last dial check. This wall grades energies one dial, which watch guarded the other. The dipole watch, stage 2, both dials audited. So bring back question 1, why does a sharper simulation always cost more time? Strike the premise. It never had to. The trade-off tracked the price of hand-picked ingredients, not of accuracy. The caterer's estimate just got sharper. And the bill barely moved. The film's anchor question, the divine function, derived for 60 years in vain. This one was learned. Before I say them, you say them, 4 ideas carried this film. The term that decides the chemistry, the deal the ladder taught, and what we struck it down to, the trick that kept the bill cheap, and the 2-part training that kept it honest. Say them out loud. I'll wait. The leftover term, accuracy bias time, struck accuracy bias data, cheap features, with points talking through hubs and 2 errors, 2 stages. Chemistry's best tool was exact except one small correction. And for 60 years, sharper meant slower. A small network learned that correction from 400,000 gold standard answers. Nearly the same speed, better answers. The rule was never a law. If you keep one word from tonight, keep the name itself. S split the energy K. Keep the ingredients cheap. AI, ask the data, not the derivation L. Let points talk through hubs. AI audit both errors. Scala. And one question to leave open. No reveal this time. If accuracy is now bought with data, the next version of chemistry's missing line is a data set away. So what measurement would it take for you to trust a learned formula on chemistry no one has ever run?